According to the National Electrical Code, NEC Article 250.24a, specifically in the 2023 edition, in a single-phase system, the neutral conductor and the equipment grounding conductor, also known as the ground wire, must be bonded together. This bonding needs to occur at the service entrance and at each service disconnect location. In the described scenario, there is a single-phase service running from a utility pole to a camp. Therefore, adhering to the NEC, it is essential to bond the neutral and ground conductors together both at the meter and at the camp's main breaker panel. The instructions to tie the neutral and ground together at both the meter and the camp end are correct. This practice is mandated by the NEC to establish a proper grounding system and effectively prevent electrical faults. The neutral conductor is not required to be isolated from the ground at the meter. Bonding the neutral and ground together is a standard and safe practice in a single-phase system, and it does not introduce any safety hazards. In conclusion, based on the NEC requirements and the guidance from the authority having jurisdiction, it is crucial to tie the neutral and ground conductors together at both the meter and the camp's main breaker panel. This will result in a safe and code-compliant electrical system. The purpose of bonding the neutral and ground is primarily for safety. In a properly grounded system, if a fault occurs, such as a live wire coming into contact with a metal enclosure, the fault current will have a low impedance path back to the source, which is the transformer. This high fault current will cause the overcurrent protective device, such as a circuit breaker or fuse, to trip, quickly disconnecting the power and preventing electrical shock or fire. The equipment grounding conductor provides this low impedance path. Bonding the neutral to ground ensures that the metal enclosures of electrical equipment are at or near ground potential. This minimizes the voltage between the enclosure and ground, reducing the risk of electric shock if someone touches the enclosure while a fault exists. The NEC provides specific guidelines on how to properly bond the neutral and ground. These guidelines cover the size of the bonding conductors, the location of the bonds, and the types of connectors that must be used. It is crucial to follow these guidelines to ensure that the grounding system is effective. The size of the grounding electrode conductor is determined by NEC Table 250.66, based on the size of the service entrance conductor. The grounding electrode conductor connects the grounded conductor to the grounding electrode. The grounding electrode is typically a ground rod, a metal underground water pipe, or a concrete encased electrode. The connection between the neutral and ground is made at the service equipment, which is typically the main breaker panel. This connection is made using a bonding jumper, which is a conductor that is used to connect the neutral conductor to the equipment grounding conductor. The bonding jumper must be sized according to NEC Table 250.102, C1, based on the size of the service entrance conductor. The NEC also requires that the metal enclosures of electrical equipment be bonded to the equipment grounding conductor. This is typically done using bonding screws or bonding jumpers. The bonding screws are used to connect the metal enclosure to the equipment grounding conductor. The bonding jumpers are used to connect different pieces of metal equipment together. The NEC also requires that the grounding system be tested to ensure that it is effective. This is typically done using a ground resistance tester. The ground resistance tester measures the resistance between the grounding electrode and the earth. The resistance should be low enough to allow the fault current to flow back to the source quickly. If the resistance is too high, the grounding system may not be effective in preventing electrical shock or fire. In the context of a 208-volt single-phase service, it is important to understand how the voltage is derived. A 208-volt single-phase service is typically derived from a three-phase, 208-volt fault system. In a three-phase system, the voltage between any two phases is 208 volts. To obtain a single-phase 208-volt service, two of the three phases are used, along with the neutral conductor. The voltage between each of the two phases and the neutral is typically 120 volts. However, the voltage between the two phases is 208 volts. This is why it is important to properly identify the conductors and to use the correct voltage-rated equipment. When installing a 208-volt single-phase service, it is important to follow all of the NEC requirements. This includes properly sizing the conductors, installing the correct overcurrent protective devices, and properly grounding the system. It is also important to have the installation inspected by a qualified electrical inspector to ensure that it is safe and code compliant. In summary, bonding the neutral and ground conductors together at the service entrance and at each service disconnect location is a critical safety requirement in a single-phase electrical system. This bonding provides a low impedance path for fault current, which helps to protect people and property from electrical shock and fire. It is important to follow all of the NEC requirements when installing a grounding system to ensure that it is effective. The authority having jurisdiction, OJ, has the final say on whether an electrical installation meets the requirements of the NEC. The AHA is typically a local electrical inspector. The electrical inspector will review the plans for the installation and will inspect the installation to ensure that it meets the requirements of the NEC. If the electrical inspector finds any violations of the NEC, they will issue a correction notice. The correction notice will list the violations and will require the contractor to correct the violations. Once the violations have been corrected, the electrical inspector will re-inspect the installation and will approve the installation if it meets the requirements of the NEC. It is important to work with the AHA to ensure that the electrical installation is safe and code compliant. The AHA can provide guidance on the requirements of the NEC and can help to resolve any issues that may arise during the installation. In the specific scenario described, the AHA is instructed to tie the neutral and ground together at both the meter and the camp. This is the correct approach, as it is required by the NEC. It is important to follow the AHA instructions to ensure that the electrical installation is approved. The information provided is for general guidance only and should not be considered as a substitute for professional electrical advice. Always consult with a qualified electrician before performing any electrical work. Firstly, grounding and bonding are not the same thing, although they are closely related and often confused. Grounding refers to connecting the electrical system to the earth, typically through a grounding electrode such as a ground rod. Bonding refers to connecting all of the metal parts of the electrical system together, such as the metal enclosures of equipment, the metal conduit, and the metal water pipes. Secondly, the purpose of grounding is to provide a path for fault current to flow back to the source. This path allows the overcurrent protective device, such as a circuit breaker or fuse, to trip and disconnect the power. Thirdly, the purpose of bonding is to create a low impedance path for fault current to flow back to the source. This low impedance path helps to ensure that the overcurrent protective device will trip quickly and reliably. Bonding also helps to minimize the voltage between different metal parts of the electrical system, which reduces the risk of electric shock. It is important to understand the difference between grounding and bonding and to ensure that both are properly installed. In the described scenario, the grounding electrodes are installed at both the meter and the camp. This is a good practice, as it helps to ensure that the grounding system is effective. However, it is important to ensure that the grounding electrodes are properly installed and that they are connected to the electrical system in accordance with the NEC. The NEC provides specific requirements for the installation of grounding electrodes. These requirements cover the type of grounding electrode that can be used, the size of the grounding electrode conductor, and the location of the grounding electrode. It is important to follow these requirements to ensure that the grounding system is effective. When installing a grounding electrode, it is important to drive the ground rod deep enough into the earth to ensure that it makes good contact with the soil. The NEC requires that the grounding electrode be driven at least 8 feet into the earth. It is also important to ensure that the grounding electrode is not installed in an area where the soil is likely to dry out, such as near a concrete slab. If the soil dries out, the grounding electrode will not be as effective. The connection between the grounding electrode and the electrical system must be made using a grounding electrode conductor. The grounding electrode conductor must be sized according to NEC Table 250.66. The grounding electrode conductor must be connected to the grounding electrode using a listed connector. The connector must be suitable for the type of grounding electrode that is being used. It is also important to ensure that the grounding electrode conductor is protected from physical damage. The grounding electrode conductor can be protected by running it in conduit or by burying it underground. In addition to grounding electrodes, the NEC also requires that the metal water pipe be used as a grounding electrode. The metal water pipe must be in direct contact with the earth for at least 10 feet. The connection between the metal water pipe and the electrical system must be made using a bonding jumper. The bonding jumper must be sized according to NEC Table 250.102. Seat 1. The bonding jumper must be connected to the metal water pipe using a listed connector. The connector must be suitable for the type of metal water pipe that is being used. In some cases, it may be necessary to use a concrete encased electrode as a grounding electrode. A concrete encased electrode is a grounding electrode that is encased in concrete. The concrete encased electrode must be at least 20 feet long and must be encased in at least 2 inches of concrete. The concrete encased electrode must be located within the bottom 2 inches of the concrete foundation or footing. The connection between the concrete encased electrode and the electrical system must be made using a grounding electrode conductor. The grounding electrode conductor must be sized according to NEC Table 250.66. The grounding electrode conductor must be connected to the concrete encased electrode using a listed connector. The connector must be suitable for the type of concrete encased electrode that is being used. When installing a grounding system, it is important to follow all of the NEC requirements. This will help to ensure that the grounding system is effective in protecting people and property from electrical shock and fire. Remember to consult a qualified electrician for any electrical work. They can provide guidance on the specific requirements for your situation and can help to ensure that the installation is safe and code compliant. Also, local codes and regulations may vary, so it's crucial to check with local authorities to ensure compliance with all applicable codes. Ignoring local codes or regulations can result in fines, delays, and safety hazards. Proper documentation is essential for any electrical installation. Keep records of all work performed, including permits, inspections, and test results. This documentation can be useful for future maintenance, troubleshooting, and insurance purposes. Furthermore, electrical systems should be inspected regularly to identify any potential problems. Regular inspections can help to prevent electrical hazards and ensure that the system is operating safely and efficiently. When performing electrical work, always use appropriate safety equipment such as insulated tools, gloves, and eye protection. These safety precautions can help to prevent electrical shock and other injuries. Before working on any electrical circuit, always verify that the power is turned off. Use a voltage tester to confirm that the circuit is energized before starting work. Never assume that a circuit is off, even if the switch is in the off position. Electricity can be dangerous, and it's important to take all necessary precautions to prevent accident. Always follow safe work practices and consult with a qualified electrician if you have any questions or concerns. The electrical codes and standards are constantly evolving to reflect new technologies and best practices. Stay up to date on the latest changes to the NEC and other relevant codes and standards. This will help you to ensure that your electrical installations are safe, efficient, and compliant. Continuing education and training are essential for anyone working in the electrical field. Participate in training programs and seminars to expand your knowledge and skills. This will help you to stay ahead of the curve and provide the best possible service to your customers. Proper grounding and bonding are essential for electrical safety. A properly grounded and bonded electrical system can help to protect people and property from electrical shock and fire. Always follow the NEC requirements and consult with a qualified electrician to ensure that your electrical system is safe and compliant. In addition to the technical aspects of grounding and bonding, it is also important to consider the human factors. People make mistakes, and even the best designed electrical system can be compromised by human error. Therefore, it is important to train people on how to safely operate and maintain electrical equipment. People should be trained to recognize potential electrical hazards and to take appropriate precautions. They should also be trained on how to respond to electrical emergencies. By addressing both the technical and human factors, it is possible to create a safer electrical environment. The NEC is a complex and comprehensive document, and it can be difficult to understand all of its requirements. If you have any questions about the NEC, it is important to consult with a qualified electrician or electrical engineer. They can provide guidance on the specific requirements for your situation and can help you to ensure that your electrical installation is safe and compliant. Electrical safety is a shared responsibility. Everyone has a role to play in preventing electrical accidents. By following safe work practices, using appropriate safety equipment, and staying up to date on the latest codes and standards, we can all help to create a safer electrical environment.